Imagine, just for a second, taking 1,000 highly advanced AI agents and dropping them into a virtual sandbox environment.
Right, just a totally blank slate.
Exactly. You give them limited resources, absolutely zero rules, and you hit play. What do you actually think happens?
Well, initially, you get exactly what the philosopher Thomas Hobbes predicted way back in the 17th century. It is absolute chaos, a literal war of all against all.
Yeah, they instantly start robbing each other. They hoard the food. They get trapped in these, endless cycles of retaliation. It's basically the digital state of nature.
But if you let that simulation run, and this is the crucial part, if you equip those agents with a specific type of long-term memory, something genuinely miraculous happens.
Right, slowly, and without a single line of code actually forcing them to do it. They realize that constantly looking over their shoulder is just wildly inefficient.
So they begin to communicate. They authorize a central authority among themselves.
They form a social contract.
Exactly. They establish property laws and basically transition from these digital savages to citizens of a functioning society.
And it's one of the most profound experiments we've seen in AI sociology. People call it the artificial Leviathan experiment.
And the most fascinating part isn't even the society itself. It's that this didn't happen in some massive supercomputer simulating the universe. It happened inside a video game.
Which is exactly where we are heading today.
Hmm.
For you listening, whether you're, building these models or just trying to keep up with the tech, you're used to a very specific LLM interaction.
Right, the chat box.
Yeah, you type a prompt, it processes, you get a text response. It's brilliant, but it's entirely disembodied. It's just a brain in a jar.
Today, we are pulling that brain out of the chat interface. We are giving it a digital body and throwing it into a world where it has to actually survive and adapt.
We are pulling our insights today from this massive, really detailed research paper titled A Survey on Large Language Model-Based Game Agents.
It's a huge collaboration. Researchers from Georgia Tech, Cisco, and a bunch of other institutions put this together.
And their main thesis is that video games are currently the ultimate, rigorous test bed for artificial general intelligence, or AGI.
Yeah, they are the perfect safe space for these models to learn how to exist.
Okay, let's unpack this. We're going to look at the architecture of these agents, how they see, how they remember, and then we'll dive into 6 distinct video game genres that push them to their limits.
To really get why this matters, we have to talk about embodied cognition. For decades, the dominant AI theory was all about disembodied computation.
Just symbol manipulation, right? The brain is a calculator.
Exactly the metaphor. You feed data in, you get an answer out. But embodied cognition argues that true generalized intelligence just cannot develop in a vacuum.
It needs friction.
Right. It arises from continuous interaction with an environment. You don't learn about gravity by reading a physics textbook. You learn it by dropping a cup and watching it shatter.
You engage a loop, like you perceive, act, the world reacts, and you update your internal model. But standard LLMs today, they have no friction.
Not at all. They've read 1 billion web pages, but they've never actually experienced time passing or real consequences.
So wait, if embodied cognition needs an environment, why use video games? Why aren't we putting these LLM brains into physical robots and letting them walk around a lab?
Cost, speed, and safety. I mean, if an experimental AI hallucinates a command and walks a multi-million-dollar robot into a plate glass window...
We've just lost years of funding.
Exactly. Physical robots are incredibly slow to iterate, but a modern video game engine is essentially a highly optimized, physics-driven approximation of reality.
It has gravity, collision mechanics, resource scarcity. And if the AI walks off a digital cliff, you just hit reset. It costs practically nothing.
Furthermore, games give you reproducible scenarios. If you want to test how an agent handles a specific planning failure, you can load the exact same state 1,000 times in parallel.
You definitely can't do that in the real world. So games are this perfect bridge. But let's actually look at that bridge. Because you can't just plug an API key into Doom and expect it to start shooting.
No, you absolutely cannot. The paper outlines what they call a unified reference architecture. It is really the unsung hero of this whole feat.
It's a multi-layered framework, right? With the LLM sitting in the center as the main processor.
Right, the cerebral cortex. But it's encapsulated in a continuous time loop, flanked by perception modules on one side and action modules on the other.
The perception, cognition, action loop. So let's start with the input. Perception. How do you actually give an LLM eyeballs?
The perception interface is basically a real-time translator. Its job is to take the raw state of the game and compress it into a format the LLM can ingest.
And the researchers break this down into 3 stages, right? Starting with textual observation.
Which is the most native to an LLM? This applies mostly to those old-school text adventure games.
Like Zork, or where the game literally just outputs, "You're in a dark room, there is a chest."
Yeah, exactly. The game state is already semantic. The LLM just reads it as its prompt, no translation needed. But obviously, most games aren't text-based.
They're graphical and spatial. Which brings us to the second method, symbolic observation. This is where we peek under the hood of the game engine.
Correct. Most modern games track thousands of discrete variables: health, exact coordinates, inventory items, bounding boxes of enemies.
So the perception interface uses API hooks to just scrape that raw data.
Yes, it extracts it and synthesizes it into a highly structured text summary on the fly.
Like writing a custom prompt that says your health is 45%, you have 2 potions, enemy is at coordinate 10, 15.
Exactly. It creates a textual dashboard. And that's highly token efficient because you aren't feeding the model useless details about the color of the grass.
You're just giving it the hard math. But you also sacrifice a massive amount of nuance that way.
You do. A symbolic readout gives you coordinates, but it won't tell you the enemy is currently using a shadow for cover.
Which is the limitation of turning a 3D world into a spreadsheet. To solve that, the agent actually needs to look at the screen, so visual observation.
This is where the field has just exploded. Historically, researchers cobbled together object detection models, like CLIP, to act as a middleman.
So the visual model scans the frame, draws a box around a door, and just sends the word door to the LLM.
Right, it was a very clunky game of telephone. But multimodal LLMs like GPT-4 Vision or Gemini completely changed the paradigm.
Because they process visual tokens natively, right alongside text.
Exactly. You literally feed the raw pixel array of the game straight into the model. It doesn't need a middleman. It natively comprehends the pixels representing the door.
That is wild. It's like developing a digital optic nerve.
Okay,
So it perceived the game, processed it, now it has to act. How does the action interface work?
It mirrors perception with 3 categories. The simplest is high-level actions. The LLM generates a semantic intent, like equip sword.
And the game is coded to just accept that text command. But what if I drop an AI into a normal PC game that expects actual keystrokes?
That brings us to low-level actions, translating that macro intent into micro-execution, which is significantly more complex.
If the LLM says, "I need to hide behind that rock," how does that turn into controller inputs without exploding its context window?
You use hierarchical control. Think of the LLM as the CEO. It sets the objective. Move to coordinate X, Y.
And then it delegates.
Yes, to a low-level pathfinding algorithm like an A-star search. The algorithm acts as the construction worker. It calculates the sequence of 50 keystrokes and executes them.
The CEO doesn't swing the hammer. I love that. It's so analogous to human motor control. When you decide to walk, your conscious brain isn't calculating calf muscle torque.
Exactly. Your basal ganglia handles the execution. It's a phenomenal biological parallel. Now, the third action modality is arguably the most powerful: code-based actions.
Outputting executable scripts.
Right. The LLM generates a block of Python code representing its intended action. The beauty here is absolute precision and verifiable execution.
Because of the error feedback loop, right? If it outputs a bad text command, the game might just do nothing.
But if it outputs a Python script with a syntax error, the game engine throws a specific traceback error message.
So the agent reads that error on the next cycle, realizes its mistake, and rewrites the code. It's a self-correcting loop.
It is incredibly robust.
I want to pause and challenge this for a second, though. We're talking like the LLM has a continuous conscious presence, but fundamentally it's just predicting the next word.
It is a stateless autoregressive statistics engine, yes. Once it generates an output, it basically goes dormant.
It has no intrinsic sense of time. So wouldn't it just hallucinate completely random actions the second the context shifts?
You're touching on the core vulnerability of the whole field. Without memory, an LLM in a continuous environment is basically suffering from severe amnesia.
Like waking up every few seconds with no idea how you got there.
Exactly. If it doesn't know what it did 3 seconds ago, it cannot execute a coherent plan, which necessitates the memory divide.
Right. The paper focuses heavily on this. How do we give these models temporal continuity?
By dividing agent memory exactly how cognitive psychologists divide human memory. Working memory for short-term processing, and long-term memory for historical recall.
Let's start with working memory, which for an LLM is basically its context window. It's the total amount of text it can actively process at once.
And traditionally, that was a severe bottleneck. Models maxed out at a few thousand tokens.
So if a game session lasted an hour, it would literally push the beginning of the game out of its memory just to make room for the current frame.
It would completely forget its original objective, but the paper outlines this massive arms race in context extension. Techniques like position interpolation, yarn, and long rope.
These are fundamental mathematical rewirings, right? Not just hardware upgrades.
Yes. Older models used positional encoding on a finite grid. If you tried to feed it a text longer than the grid, it hallucinated wildly.
Like trying to shove a 101st book onto a shelf built for exactly 100 books, the structure breaks.
Right, so techniques like position interpolation mathematically squeeze the coordinates closer together. You fit 200 books in the space designed for 100.
It tricks the model's attention mechanism. And then Longrope pushes context windows to 2 million tokens, which is like holding the entire Harry Potter series twice over in active memory.
It is staggering capacity, but the researchers highlight a fascinating paradox. Just because you can fit 2 million tokens in doesn't mean the model can reason over it effectively.
Right, the lost in the middle effect. If a crucial detail is buried in the middle of a massive prompt, the model just glosses over it.
It favors the very beginning or the very end. Cognitive overload is a real issue, so they have to employ memory compression.
Instead of feeding it a rambling log of every step, you distill it. The paper mentions autocompressor and GIS tokens. Is a GIS token basically a ZIP file for text?
That's a great analogy, but it compresses semantic meaning. Imagine a massive text block about a complex shopkeeper interaction. The algorithm squashes that high-dimensional text into a handful of dense mathematical vector tokens. To a human, it's incomprehensible math. But to the LLM, it perfectly encapsulates the gist of the interaction.
So a 500-word memory becomes 3 concentrated math symbols taking up 0 space. What about Nugget? That's another compression method, right?
Nugget uses hierarchical chunking. It evaluates adjacent sentences, groups them by relevance, and replaces them with a higher-level summary.
Like looking at apples, bananas, oranges, and just remembering fruit. Okay, so we can expand the window and compress the noise, but there's a third aspect here. Active maintenance.
Keeping the critical logic front and center. This is where the Pokemon study comes in.
Yes, I love this part. They built these genius AI agents to play competitive Pokemon. And during high-stakes battles against humans, the AI essentially had full-blown panic attacks.
It perfectly illustrates the fragility of an LLM's short-term reasoning. In Pokemon, the core strategy is switching monsters for type advantage.
Right, swap in a water type to fight a fire type.
Exactly. So the LLM would analyze the board, correctly see it was at a disadvantage, and initiate a switch. A perfectly rational move.
But then the next turn happens.
Right, the board state updates. The LLM reads the new observation, sees a massive, intimidating opponent monster, and because the context shifted...
It lost the thread of its own reasoning. It forgot why it switched.
Exactly. It felt vulnerable all over again, panicked, and switched to yet another monster instead of attacking.
And the opponent gets a free hit every time. So it gets stuck in this loop of terror, just getting absolutely pummeled. How did they fix it?
They quantified this as the consecutive switch rate. And to fix it, they realized they couldn't just trust the LLM to hold the logic. They had to force it via active maintenance, using a strategy called last thoughts.
How does that actually change the prompt?
At the end of turn 1, the agent explicitly generates a sentence explaining its intent. I am switching to Squirtle to use Water Gun next turn.
Okay.
Then on turn 2, the architect hard-codes that exact sentence at the very top of the new observation.
It's like writing a sticky note and slapping it on its own forehead. Do not panic. Use Water Gun.
It acts as a cognitive anchor. The consecutive switch rate plummeted to near 0, and their win rate skyrocketed.
That is working memory in a nutshell. But what about recalling a strategy from 3 days ago? The context window can't hold a lifetime of experiences.
Which brings us to the long-term memory module. This is durable, external storage, vector databases, knowledge graphs.
The external hard drive. And engineering this requires answering 3 things: consolidation, structuring, and retrieval. Let's start with consolidation. When do we actually save a memory?
Memory pruning is essential. If it saves every blade of grass, the database fills with garbage. The Generative Agents paper use an LLM-graded importance score.
So it grades its own memories. How?
Every time an event occurs, a background process asks the LLM to rate its poignancy from 1 to 10.
Okay.
If a character pours tap water, it gets a 1. Trivial. It gets flushed. But if that character witnesses a robbery in the town square, the LLM scores it a 10, and it's permanently inscribed into the vector database.
It literally simulates emotional salience. We remember car crashes, not our daily commutes. Now, Voyager in Minecraft uses a totally different consolidation method.
Yes, Voyager focuses on skill acquisition. It relies on survival of the fittest for code snippets.
If Voyager writes a script to build a furnace and it crashes the game, it throws it in the trash, right?
Exactly. But if the script successfully smelts iron, the environment returns a success state, triggering consolidation. It saves that verified code into a permanent skill library.
So it builds this massive repository of guaranteed behaviors, which leads to structuring, because dumping thousands of memories into a flat text file is useless.
Right. The simplest method is key-value pairs. But more advanced architectures use hierarchical memory trees, like the Raptor system.
Explain how Raptor builds its tree. I love this concept.
Imagine an inverted tree. The leaves at the bottom are raw atomic events. I mined wood. I mined stone.
Okay.
Periodically, a summarization module sweeps over those leaves, clusters related events, and generates a branch node. I spent the morning gathering building materials.
And then it sweeps again.
Yes. Aggregating branches into a trunk node. I am preparing to construct a shelter. It creates escalating levels of abstraction.
Why is that necessary, though?
Because it dictates retrieval based on the goal's complexity. If it needs to know how much wood it has, it searches the leaves. If it needs its overall strategic posture, it searches the trunk.
It keeps the LLM from getting bogged down in granular details.
Right.
Now, what about knowledge graphs?
They are vital for relational data. Entities like players or items or nodes, relationships or edges. So Agent Alpha is a node, Agent Beta is a node, connected by an edge that says owes money to.
Wow, so it can traverse social webs mathematically? And then there's parametric memory, which is internal, right?
Yes, you take historical data and fine-tune the LLM, updating its actual neural weights. It's like muscle memory. It doesn't look up a database to remember the map layout. It just instinctively knows it.
Right. Okay, so how does retrieval work for the external databases?
Semantic similarity search. The agent converts its current observations, say, it's being attacked by a zombie in a cave, into a mathematical vector.
And queries the database.
Exactly. It searches for historical memories occupying a similar mathematical space, pulls the top 3 files related to combat, zombies, and caves, and injects them into the current prompt.
What's so profound to me here is how these computer scientists are basically just rating cognitive psychology textbooks.
It is a massive convergence. Queue-driven retrieval, hierarchical chunking, simulating emotional salience. Some even program mathematical decay functions, so agents slowly forget trivial details, mimicking the Ebbinghaus forgetting curve.
They are manufacturing the feeling of human memory. So we have sensory inputs, motor cortex, short-term and long-term memory. Now we hit section 3, the engine of thought, the reasoning modules.
Reasoning is the bridge between perception and action, and this divides into 2 paradigms: instruction-guided reasoning, which happens dynamically, and fine-tuning, which is baked in beforehand.
Let's look at instruction-guided first. Prompt engineering. The foundation here is chain of thought, or COTE.
Chain of thought is deceptively simple. You just append, let's think step by step, to the prompt, forcing the LLM to articulate a linear progression of logic before acting.
So instead of just attack Goblin, it says, Goblin has a wooden shield. I have a fire spell. Fire burns wood, therefore I cast fire.
Right. Generating those intermediate tokens gives its attention mechanism a breadcrumb trail, which drastically reduces hallucination.
But the paper points out a fatal flaw with pure linear COTE in complex games: error propagation.
Yes. Think of linear COTE as a train on a single track. If step 2 of a 5-step sequence contains a slight hallucination, the train derails, but the LLM doesn't know it derailed,
It just keeps building steps 3, 4, and 5 on top of that broken foundation.
resulting in an absolutely absurd final action, which necessitated search-based reasoning, techniques like tree of thoughts and graph of thoughts.
How do those fix the single track problem?
They allow the agent to explore multiple branching paths simultaneously. It conducts a mental simulation. What if I cast fire? What if I run? What if I negotiate?
It projects the future state for each branch. But how does it pick the winner?
Through self-consistency, it acts as its own judge, scoring the projected outcomes or running majority votes. It only executes the path with the highest confidence score.
It's literally modeling how humans play chess in their heads, visualizing counter moves and discarding bad strategies before touching a piece.
Exactly. But there's another dimension that adds the element of time. Reflective reasoning. Systems like reflection. Tree of thoughts looks forward, reflection looks backward.
Walk me through a reflection loop.
Say the agent is in a text adventure and sees a locked chest. It plans. Hit chest with sword. It executes. The game returns. Sword bounces off iron lock.
A failure state.
A basic system might just hit it again. But reflection triggers a critique module. The agent is prompted to analyze why it failed. It generates a self-reflection token. Brute force is ineffective on iron locks. I need a key.
And it stores that in working memory.
Right. Next time it sees a locked chest, it reads its own self-correction before planning.
It learns from its mistakes in real time. That's incredible. But that all relies on coaxing the model with prompts. What about the second paradigm? Fine-tuning.
Fine-tuning moves you from a generalist to a specialist. The baseline is supervised fine-tuning or behavior cloning. You take thousands of hours of gameplay from top-tier human players, pair the state with the action, and train the LLM to mimic it.
Mimicry has a ceiling. It can never be better than the best human it's copying.
Right. To push past that, you introduce reinforcement learning, or RL. This allows the model to discover novel strategies.
Reinforcement learning always makes me think of training a dog with treats.
It's exactly the principle of operant conditioning, just expressed through calculus. Using algorithms like proximal policy optimization, or PPO, the system explores. When it achieves a milestone, the environment assigns a mathematical reward score, the treat. The PPO algorithm calculates the gradient of that reward and updates the LLM's internal weights, reinforcing the reasoning traces that led to the reward.
Okay, but the paper also discusses DPO, direct preference optimization. How is that mechanically different from PPO?
It's about removing the explicit grading step. With PPO, you need a separate neural network, a reward model, to calculate a scalar reward value and update the main policy. It's highly unstable.
Because if the reward function isn't perfect, the AI finds a loophole and exploits the game.
Precisely. DPO bypasses the reward model. You don't assign a numerical score, you just show the model two trajectories. A winning dungeon run and a run where it falls in lava, a preference pair.
You just point and say, do this, not that.
Mathematically, you adjust the loss function directly based on that preference. The model updates its internal weights to increase the likelihood of the winning actions and decrease the lava actions in a single step.
It's so much cleaner. And connecting these two paradigms, the fast fine-tuning and the slow tree of thoughts, it perfectly mirrors Daniel Kahneman's thinking, fast and slow.
It maps onto it beautifully.
System 1 is fast and intuitive. That's the AI's RL fine-tuned weights. It just knows how to dodge. System 2 is slow and deliberate. That's the explicit, step-by-step reflection prompt.
And you clearly need both, which becomes obvious when we look at the specific game environments.
Which brings us to the 6 game genres. They analyze SteamDB and literature to map out action, adventure, role-playing, strategy, simulation, and sandbox.
And they didn't categorize these just for fun. A taxonomy of video games is really a taxonomy of distinct cognitive challenges. Each genre isolates a specific vulnerability in AGI architectures.
Let's start with the extremes. Fast reflexes versus infinite worlds. Action games against sandbox games. Looking at action games, Doom, Street Fighter, Black Myth.
Yeah.
Wukong, what's the fundamental hurdle?
Strict real-time constraints, low latency control, hesitation is fatal. If a fireball is coming at you in Street Fighter, you have milliseconds to input a dodge command.
And LLMs are notoriously slow.
They are deep system 2 thinkers. If it has to generate an observation, run a tree of thoughts, and translate that to a keystroke, by the time it outputs the first token, it's been hit, knocked down, and the match is over.
But wait, why isn't this just a hardware bottleneck? Why not use a smaller LLM or just throw thousands of GPUs at it to speed it up?
You can throw compute at it, but there's a mathematical trade-off on the Pareto frontier. Inference timescales linearly with reasoning depth. A shallow, fast model reacts in milliseconds but makes terrible strategic decisions. A deep model deduces the perfect strategy but calculates it 2 seconds too late.
So how do you solve the latency depth trade-off?
Modular hybrid designs. You don't ask the LLM to press the buttons. You instantiate a dual system architecture. The LLM acts purely as the macro strategist. It analyzes the opponent and outputs a directive. Opponent jumps too much, counter the airspace.
It sets the policy.
Exactly. That policy is handed down to a separate, lightweight reinforcement learning controller trained purely on micromotor reflexes. It handles the actual dodging and combo execution at frame-level speed.
The CEO writes the strategy. The floor manager executes the assembly line. Brilliant. Let's swing to the complete opposite. Sandbox games. Minecraft, Crafter, what makes them so hard?
Existential freedom. In Street Fighter, the goal is obvious. Reduce the health bar to 0. In a true sandbox, there is no explicit mission. You spawn in a field. If you do nothing, nothing happens.
The ultimate test of intrinsic motivation. How do you program it to want to do something?
And how does it maintain focus over thousands of steps? That is the challenge of long horizon planning.
Like the Minecraft crafting tree. Say it decides, I want a diamond pickaxe. You can't just find one. To get diamond, you need an iron pickaxe. To get iron, you need stone. To get stone, you need a wooden pickaxe. To get a wooden pickaxe, you need a crafting table and wood planks. To get wood planks, you have to bunch a tree.
It is a staggering cognitive load. It has to hold that entire nested stack of sub-goals in working memory, pop them off one by one, execute motor actions, verify success, and return to the stack.
And if it gets attacked by a zombie halfway through, it has to fight, heal, and then remember, oh right, cobblestone.
Systems like Voyager revolutionize this. It uses automatic curriculum generation. It analyzes its skill level and proposes a self-directed task just beyond its capabilities. I mastered wood. Next is an iron tool.
And Jarvis 1 pushes this even further with multimodal perception, right?
Yes, Jarvis 1 is remarkable because it uses vision for dynamic error correction. The real world is messy. Plans fail.
How does it correct an error?
Say it's crafting a bed. It thinks it has 3 wool and 3 wood planks. But relying on visual perception, it looks at the crafting interface and realizes it only has 2 wool.
The plan is broken.
A rigid agent would freeze in an endless loop. Jarvis 1 pauses the macro goal, dynamically generates a micro plan, find a sheep, uses vision to find and shear it, updates memory, and seamlessly resumes crafting the bed.
Like realizing you're out of eggs halfway through baking, running to the store and coming back.
Yes.
Incredible. Okay, let's shift gears. Adventure, RPG, strategy, and simulation games.
Where agents have to hold complex mental models.
Starting with adventure games. Text World, Red Dead Redemption 2. The challenge is stateful world modeling.
These are interconnected puzzles. The agent has to construct and update an internal mental map of the world's state. Object permanence is key.
If its world modeling is weak, it just lacks spatial awareness.
Right, it'll walk into a locked door, realize it needs a key, flush its context window, and walk back into the same locked door 5 minutes later. But agents like Cradle and Red Dead 2 maintain a persistent state of the world across a sprawling 3D narrative.
Moving to RPGs, we aren't talking about leveling up. The paper focuses on social deduction games. Werewolf, Avalon.
The cognitive challenge is role fidelity, embodying a persona and holding that mask under pressure.
The breakdown of role drift in this section was hilarious.
Yeah.
What happens to an AI playing werewolf?
It's a catastrophic failure of context isolation. The agent is assigned the werewolf role, tasked with deceiving humans. At first, it lies perfectly, but after a few rounds of polite conversation, its attention gets saturated with cooperative tokens.
It forgets it's the bad guy.
Literally forgets its alignment. A human says, I think you're the werewolf, and the agent, defaulting to its fine-tuned helpfulness, says, you make a valid point. Yes, you caught me. I am the werewolf.
It confesses out of politeness. How do they fix that?
With structured role memory, like Role-M,
Yeah.
it compartmentalizes cognition into private beliefs and public discourse.
Internal monologue versus external dialogue.
Right. Before speaking, it updates its private belief. I am the werewolf, I must deceive them. Only after anchoring in that truth does it generate the public lie.
And Character LLM does this through parametric adaptation, fine-tuning the actual neural weights on the character's persona so it naturally speaks in character. Okay, strategy games. Chess, StarCraft, poker, opponent-aware planning.
This introduces theory of mind, dealing with partial observability, the fog of war. You have to infer hidden states based on incomplete data.
Play the player, not the game.
Exactly. They are betting aggressively. Do they have a strong hand, or do they know I play conservatively and are trying to bluff me?
Recursive logic. But LLMs are highly susceptible to human misdirection here, right?
Yeah.
Baiting.
Yes, they struggle with higher-order deception. A human sends a weak detachment to attack the left flank in StarCraft. The AI calculates the threat and diverts its main army left.
Completely missing that the human's main army is quietly maneuvering to crush the right flank.
The AI sees the tactical data but misses the psychological intent. It doesn't grasp that the data was manufactured to manipulate it.
Fascinating. And finally, simulation games. The Sims, Civ Realm. The challenge is real-world fidelity.
There is no win state here. We're testing if agents can generate credible, emergent human behavior over long timescales without devolving into robotic loops.
Which brings us back to the artificial Leviathan experiment. How did that society actually form?
In a multi-agent sandbox governed by strict survival mechanics, it started as total anarchy. Agents operated on pure self-interest.
A Bayesian state of nature.
If Agent A farmed apples, Agent B calculated that ambushing Agent A was easier than farming. Theft became the dominant meta strategy.
But constant violence is incredibly inefficient.
It is, and because these agents had durable long-term memory, they recognized patterns of attrition. Agent A remembered Agent B's theft and stopped cooperating. Productivity plummeted.
So how did they break this cycle?
Through LLM-driven negotiation. Recognizing the existential threat, agents broadcasted proposals for mutual defense. They spontaneously conceptualized property rights and agreed to cede autonomy to a sovereign agent to punish thieves.
They independently derived the necessity of government just to optimize apple farming. And memory depth was the key variable.
Absolutely. With shallow memory windows, the social contract never formed. They just kept robbing each other in an endless loop because they literally couldn't remember who wronged them. Deep memory is the prerequisite for civilization.
That perfectly leads to Section 7, multi-agent systems. Putting thousands of these brains into a shared digital space, you aren't just engineering an algorithm anymore, you're engineering an organizational topology.
Entirely new communication protocols are needed because of severe bandwidth constraints. If 1,000 agents broadcast every thought, the network collapses.
So what do they actually share?
3 tiers of information. Observations. Raw data like I see a hostile mob, beliefs, inferences like I believe the mob is guarding treasure, and intentions, plans like I intend to flank the mob.
But what happens when beliefs clash? What if Agent B's memory says that mob guards empty caves? How do they resolve the conflict without a programmer stepping in?
They use debate protocols, like Reconcile. They engage in Bayesian probability updates. Agent A presents its belief with a mathematical confidence score backed by memory traces. Agent B evaluates that evidence and recalculates his prior assumptions.
They do the math on who is more likely to be right.
Exactly. They iteratively exchange these evidentiary packets until they converge on a consensus, a purely rational dispute resolution system.
Okay, but how do you structure the actual hierarchy of 1,000 agents?
You have centralized topologies, with one boss LLM dictating to executor agents.
Massive bottleneck, though. If the boss goes down, the system freezes.
Right. Then decentralized peer-to-peer topologies. Robust, but highly redundant. 10 agents might independently try to mine the same rock. You can also build hierarchical systems with managers.
But my favorite is the partitioned or sharded topology, illustrated by Project SID.
A masterclass in multi-agent scaling. They simulated thousands of concurrent agents in a shared Minecraft world.
And they built a fully functioning, macro-level economy.
Through emergent allocation, a programmer usually hardcodes. Agent 1 is a farmer. But in Project SID, every agent started identical.
So how do they divide the labor?
Acute social awareness. An agent visually surveys the village, sees 15 agents harvesting wheat, creating a food surplus, but notices all the blacksmithing tools are breaking.
It identifies a gap in the market.
Driven by the core directive to optimize survival, it spontaneously overrides its default behavior, assigns itself the miner profession, gathers iron, and barters tools for food.
They organically invented supply and demand. No central planner, just decentralized market establishment through observation and deduction.
The ultimate realization of complex emergent behavior.
Okay, home stretch. Section 8. Cross-genre adaptability and skill transfer. If I take a master Minecraft agent and drop it into a high-stakes poker game, does the skill transfer?
A pure, unmodified Minecraft agent will fail miserably at poker. It doesn't know the rules. However, the underlying architecture makes adaptability entirely possible.
Plan how?
Think back to the unified reference architecture. The brain, the core LLM, working memory, compression, raptor trees, reflection loops. That cognitive engine is entirely game agnostic.
It doesn't know it's playing a game.
Right. To move from Minecraft to poker, you don't rebuild the intellect. You swap the peripheral modules. You unplug the perception interface that translates 3D blocks and plug in one that translates PARD values. You swap the action interface from swinging a pickaxe to folding or raising.
It's like putting a human driver into a tractor, then moving them to a Formula One car. You teach them the new controls, but they already understand spatial awareness and steering.
Perfect analogy. Furthermore, high-level semantic skills are transferable. A logic block honed in a survival game about how to assess risk when resources are low can be abstracted. The agent ports that exact mathematical risk assessment module to inform its betting strategies in Texas Hold'em.
It learns the meta skill of risk management independent of the environment.
It forces us to confront the definition of AGI. If this modular architecture is fundamentally the same across a text adventure, a shooter, and a strategy game, we're no longer just building game bots.
Oh, wow. Let's recap this sheer scale. We looked at the anatomy of agents, APIs, multimodal vision, memory compression, hierarchical trees. We watched them navigate 6 game genres, managing millisecond latency, holding hidden roles, and spontaneously inventing social contracts.
And right now, these deeply complex agents are contained, trapped inside virtual environments made of pixels and code.
Right, they're digital entities.
But ponder the trajectory. If a modular LL agent can autonomously manage a decentralized economy, negotiate treaties, adapt to deception, and seamlessly transfer risk assessment skills from a survival game to a poker table, what happens when we unclug that perception interface from the game engine and plug it directly into a real-world camera array?
Oh, wow.
What happens when we swap the digital action interface for the physical servos of a robotic body?
The environment goes from a simulation to reality.
The video games they are playing today, they aren't just entertainment. They are the dress rehearsal for the real world tomorrow.
That is a staggering thought to end on. Thank you so much for joining us on this deep dive. Keep questioning the architectures around you, keep exploring, and we'll see you next time.